Okay, let's keep the ball rolling. Here is section 2, all about electronegativity. It is the ability of an atom and a molecule to attract shared electrons to itself. So which atom in our molecule wants the electrons more? Okay, which one is hogging them? Which one is keeping them closer to it and not sharing very well? For a molecule of HX, H being hydrogen and X being just some random element, okay, it's not saying exactly what it is, just hydrogen bonded to another element. The relative electronegativities of the hydrogen and the other X atom are determined by comparing the measured HX bond energy with the expected HX bond energy. On the periodic table, as we move from left to right across the period, electronegativity increases. And as we move down a group from the top of the periodic to the bottom of the periodic table, electronegativity decreases. The ranges of electronegativity range from 4.0 for fluorine, which is the most electronegative, to 0.7 for cesium and francium, which are the least electronegative. Okay, fluorine really wants that electron all to itself, and so it will pull that electron closer and closer to it. It doesn't share it very well. Cesium and francium, they share pretty well. They're like, yeah, if you want it, you can have it, okay? I'd still like to see it occasionally, but, you know, you can keep that electron most of the time. Here we have a diagram showing the electronegativity values for some of the elements on the periodic table. It's not all of them. You'll notice that we're missing the lanthanides and the actinides down here. You'll also notice that fluorine is the most electronegative. It has a 4.0 electronegativity value, whereas francium and cesium over here, they have 0.7. Okay, they're not very electronegative. Concept check. If lithium and fluorine react, which one has more attraction for the electron? Well, it is fluorine. Okay, because fluorine has an electronegativity of 4. Okay, it really wants that electron. Lithium's like, yeah, you can have it. Okay, so why? Well, both have valence electrons in the same principal energy level, so they're in the same period, they're in the second period, but fluorine has a greater number of protons in its nucleus. So it has more of a positive charge in its nucleus, so it can draw that electron to it much more than the lithium. And a bond between fluorine and iodine, which one has more attraction for the electron and why? Well, fluorine, once again, it is the most electronegative element on the periodic table. In this case, the nuclear charge of iodine is greater, but the valence electrons are at a much higher principal energy level, meaning they're further from the nucleus, so it's harder for that positive charge within the nucleus to attract that electron to it. So because fluorine has so few energy levels, it can draw it much more closely to it. Alright, so what is the general trend for electronegativity across rows and columns of the periodic table? Well, as we move from left to right, because the number of protons increases, so the positiveness of the nucleus, as that increases, then that increases our electronegativity because it's easier for them to attract the protons to it. As you move down the periodic table, because the size of the atom is increasing, so you're adding more and more energy sublevels, it kind of shields that positive charge and makes it harder for that nucleus to attract the electrons to it. So the electronegativity goes down as you go further from top to bottom, as you go down the periodic table. So the polarity of a bond depends on the difference between the electronegativity values of the atoms forming the bond. So if you're forming a molecule of oxygen, which is O2, then there's no difference in the electronegativity, so that is a non-polar covalent bond. A polar covalent bond is when they share that electron, but one of them holds on to it a little more tightly, so it has more of a negative charge. It's not a completely negative charge, it's just a little bit more negative on this side and a little bit more positive on this side. With an ionic bond, there's no sharing of that electron, okay? One atom possesses it. It does not let the other one have it. But because it is negatively charged, it's attracted to the positively charged atom that it took the electron from. So here are the relationship between electronegativity and bond type. A covalent bond, if there is zero difference between the binding atoms, between the atoms that are bonding, then it has a greater covalent characteristic. So it has the general characteristics of a covalent bond. It has no ionic characteristics. So it has none of the characteristics of an ionic compound. If it's a polar covalent bond, then there's an intermediate difference between the electronegativities, and it's kind of in the middle. It has some of the characteristics of a covalent charge, of a covalent bond, but it also has some characteristics of an ionic bond. And if there's a very large difference between the electronegativities of the atoms, then there is a large difference, and it is an ionic bond. And it has no characteristics of a covalent bond. It is completely ionic in its characteristics. So arrange the following bonds from most to least polar. So the most polar would be carbon and fluorine, followed by nitrogen and fluorine, and then oxygen and fluorine, because the electronegativities are so great. Then we have silicon, fluorine, carbon, fluorine, and nitrogen, oxygen, followed by boron and chlorine, sulfur and chlorine, and then chlorine, chlorine. All right, this is the least polar because chlorine bonding with chlorine, there is no electronegativity difference there. Concept check. Which of the following bonds would be the least polar and yet still be considered covalent? Well, magnesium is a metal and oxygen is a nonmetal, so we know that that's going to be an ionic bond, so we can get rid of that one. Carbon and oxygen, they have similar electronegativities. Oxygen and oxygen is going to be a nonpolar covalent bond. Silicon and oxygen, they have similar. And then nitrogen and oxygen. So if we compare the electronegativities, they are, so the nitrogen and the oxygen have the greatest difference in their electronegativities.